And welcome to our first topic of Geology 100 lecture. And today I want to briefly talk about the main points within our first chapter. This chapter is the beginning geologic theories and Earth's place in space. We've talked a little bit about who geologists are, who scientists are. Now, geologists, like many scientists, observe. We observe the rocks around us. We observe the landscapes. We also observe the systems in which we reside. Most specifically, we observe how they interact with one another. Thousands and thousands of years ago, our earliest scientists, astronomers, noticed many peculiar things in the world around us. One of them being all of these beams and these points of light that would shine at night, stars. So they begin to wonder, where does this planet that we reside on move and reside in with respect to another really big star like the sun? One of the earliest theories about Earth came around the 2nd century. An astronomer and a scientist named Ptolemy of Alexandria. Now, Ptolemy of Alexandria developed the geocentric model. Now, this model, this theory, would exist for about 14 more centuries after it was first adopted as a theory. The geocentric model essentially states that the Earth is the center of our solar system. Ptolemy of Alexandria believed that everything revolved around Earth, that Earth was the center of it all. This was largely adopted because he was able to provide a bunch of equations that essentially supported this theory of geocentrism, it is known. Where geocentrism, geo, Earth, being the center of it all. Now, at 2nd century BC, if any modern citizen at that time were to not adopt this theory and thus reject this theory, they'd be charged with heresy, right? They'd be charged with the crime. Ptolemy of Alexandria's geocentric model existed up until about the 16th century. And it really became frothy and brought to light during the Dark Ages. But it wasn't until the Renaissance when another scientist came through, Nicholas Copernicus, and noticed a couple things. And one of those being that believed that the Earth was not the center of our solar system, rather that the sun was the center of the solar system. Alongside the work of Nicholas Copernicus was also another scientist, Galileo Galilei. After Nicholas Copernicus and Galileo Galilei both built off of each other this idea of heliocentrism, this idea that in fact the sun is the center of our solar system and we on the Earth simply orbit around it, came the work of two more scientists. One was Johann Kepler, who recognized the elliptical patterns of all these planets that were orbiting around the sun, including the Earth. The Earth, thus, orbiting around the sun in an elliptical pattern. And then eventually came the work of Sir Isaac Newton, who you may all know, who was big as far as the theory of gravity and gravitational forces. We'll talk more about Sir Isaac Newton in our next lecture when we talk about the theory of continental drift and the beginnings of studying the Earth. And he comes into play when we were first trying to decide, geologists and other scientists, were first trying to observe and discern the mass of the Earth and actually how big it was in the first place. If we look, here are two great depictions of these models. On the left here, we have the Ptolemaic model, which existed for 14 centuries, right? So on the left here, this idea that the Earth was the center of the solar system, everything orbited around it. Then became the Copernicus model, or the heliocentrism model, where the sun was actually the center of the solar system, and thus everything was simply orbiting around it, including the Earth. Copernicus's model became more well adopted, especially with the working of Johann Kepler and Sir Isaac Newton. And we'll talk a little bit more about this throughout the semester. The next several slides talk about 6 major scientists that I want you all to know and to memorize. Their names, but also their most significant contributions to geology, all right, and earth sciences in general. One of your assignments that will be due at the end of this topic will be a chart that outlines these 6 scientists and the importance of their work. I ask that you complete that and turn that in on Canvas, and this will be a simple grade, all right? But I don't want you to forget these 6 scientists. I want you to keep this chart nearby as they will show up on the exam, but also their works are things that we are going to touch on through the entirety of this semester, all right? Starting with the work of Nicholas Copernicus. That brings us to our second major topic of this module, cosmology and the birth of the earth, the cosmos, right? You've all probably heard of the Big Bang Theory, right? I'm not talking about the TV show. I'm talking about this idea that everything that resides in our universe nowadays started off as an infinitesimally, very small point, 13.7 or 13.8 billion years ago. Today, 99.8% of the mass of our solar system resides in the sun itself. The remaining 0.2% resides in the other planets that orbit it, so Earth, Mars, all these other planetesimals. When we hear the Big Bang Theory, you probably think of this as an explosion. And yes, that is the most basic way to talk about the Big Bang Theory. But instead of thinking about an explosion, I want you to think about as an expansion, all right? Imagine our universe nowadays with all of the galaxies, you know, the millions of solar systems that exist out there. And we are just a speck in the universe. But 13.8 billion years ago, before the universe is what it is today, was packed into this infinitesimally small point. Smaller than an atom. This thing packed all of the energy, all the planets that we now see nowadays, these stars, these asteroids, these meteorites. They're all packed into this one very, very, very small point. This point, this extremely small ball, we can also call it a singularity. It was in an instance of the singularity where this entire universe that we now see today was packed into it, exploded, and it expanded. Once it expanded within the matters of the fractions of a second, released an immense amount of heat and light. There was no matter present in the first instances of this expansion. The only thing that were present was heat and light. Now, light being photons, so it's just a simple particle, not necessarily a piece of matter, just a simple particle, all right? So what we had is within the first instances of this expansion of this singularity was heat and light. It wasn't until a few minutes later where we actually started to create matter that we know of today, or something very close to it, right? We had nuclei that were bouncing around in this now rapidly expanding and hot universe. These nuclei were protons and neutrons and electrons. Some of these protons and neutrons in all of this chaos and this bouncing around and mixing latched on to one another. The first particles of matter that we had were isotopes of hydrogen, deuterium, and tritium. Once these deuterium and tritium were forming, they would then collide with each other, and then we started to create helium, right? But the first moments, and for the longest time, the only thing that was bouncing around in now this universe were these protons and neutrons and electrons, right? Creating hydrogen and helium. This was the first amount of matter. Now these matter, this hydrogen and helium, would then go on and to create gaseous nebulae that would form and collapse and form and collapse. So imagine this universe where all we had were these very, very small particles, these atoms that were just bouncing around in all of this chaos and spewing away from where the singularity first expanded in its first instances. After hydrogen and helium, we then create several other elements, lithium. Thus, we have the birth of some of the other common elements that we see in our periodic table of elements. For a majority of this beginning period, we only had these gaseous light elements all the way up to element number 5. We call this the Big Bang nucleosynthesis, right? Synthesis being coming together and creating, and the nucleo being the nuclei of each one of these particles. They were coming together and creating. For the longest time, we were just generating a ton of these really gaseous elements. These gaseous elements in the state of this expansion of the universe that was once really, really hot, right? It also was relatively cooler than when it first started. So the universe was expanding very rapidly, but also cooling very rapidly, cooling to the point where we could start to create some of these atoms and these nuclei. These gaseous nebulae were just creating and forming throughout the entirety of the expansion, this very rapidly expanding universe that was also cooling at the same time. The hydrogen formed these hydrogen molecules that are essentially the fuel of these stars, these gaseous nebulae. And these atoms and molecules, they coalesce to form these nebulae in the first place. Now, ultimately, gravity caused these gaseous nebulae to collapse. And the collapse caused an increase in temperature and density and rate of rotation. Now, some of these gaseous nebulae would become so big that they would form essentially the supernova, essentially what would become our stars. And one of our most famous stars that we know of today is the sun. These giant supernovae would form these giant stars. During the formation of these supernovae, we started to create elements from 6 to 26, all of these heavier elements. But once they would hit element number 26, iron, that's where it would stop. The elements, the atoms would become too heavy. There wasn't enough energy. There wasn't enough nuclear energy in order to fuse these molecules together in order to form these heavier elements. Some of these supernovae got very, very big. Eventually, one of them became what would be known as our protostar, that would eventually become our sun. These gases, all these elements started coalescing together and formed this ball. And as we know, as gravity, especially gravitational forces, all the heavy stuff wants to force itself to the center. Now, densities, we know the heavy stuff forms itself to the center. Now, imagine start spinning it. What do you think happens? All the heavy stuff goes to the center, all the light stuff gets pushed out to the edges. And that's essentially what happened here with our protostar, right? We had all the heavier elements start to go together as this thing was spinning. All the lighter stuff got pushed out to the edges. And eventually we would form these rings. And within these rings, those heavier elements would then coalesce together. And some of them would become so big the gravitational forces would then cause these other elements to come on in it as well. All right. Ultimately speaking, it was the collapse of this supernova and of these supernovae that would create the much heavier elements that we see today. So the formation of elements 6 through 26, we call that phase of the formation of elements stellar nucleosynthesis. The collapsing of eventually these supernovae that would come out from the stellar nucleosynthesis, we call that the supernovae nucleosynthesis, right? So you have 3 main phases to look at here. All right, 3 main phases of the formation of nucleosynthesis. The first one was the Big Bang, with elements from hydrogen all the way up to element number 5. And then it wasn't until stellar nucleosynthesis we get the creation of elements 6 through 26. And then everything above 26, all the heavier elements would form during the collapsing of these supernovae. As we move on in this PowerPoint, there will be several videos in here that will explain the formation of the universe during the Big Bang, the formation of our solar system, right? The starting of this protostar, this very dense ball of matter that coalesced together, that would spin around and become our protostar. And eventually, millions of years down the line would thus become the birth of our solar system, right? As you move on in this PowerPoint, I want you to just click through all the slides and really become familiar with these 3 phases of nucleosynthesis. At the end, I'll also attach a little bit more videos and some other readings for you guys to go through that will be helpful for study purposes. But the main points are going to be the 6 major scientists: heliocentrism, geocentrism, the basic workings of the Big Bang, and how and when our elements formed in the birth of the universe and thus the birth of our solar system. Later on in the slide, there's also a really good depiction of what I just explained about the formation of our solar system as well. Scientists have dated some of these meteorites that they think were forming at the same time in these rings of these planetesimals, where these protoplanets, where these larger clumps of material would coalesce other material together. But not everything got clumped into these planets, these planetesimals on these rings. Those other things that didn't get clumped in are these meteorites. And so they dated them about 4.57 billion years ago is their formation, which means that after the birth of the universe 13.7 billion years ago, it wasn't until about 9 billion years later that the solar system that we know today, that we reside in, was actually formed. Shortly after the formation of our solar system, about 4.57 billion years ago, became the birth of our Earth, about 4.56 billion years ago. There's also a few other resources at the end of the PowerPoint here that I highly suggest that you click on, and I'll also add a bunch more into the module on your Canvas page. Like always, if you have any questions about this or want a little bit more explanation, I will be hosting office hours and we could talk a little bit more about the Big Bang, the formation of our solar system, and also the 6 scientists that we as geologists have based a lot of our work off of.